All right. Hi, everyone. Today we are very happy to have Cyuan-Han Chang from University of Chicago visiting us. He is going to be talking about graviton loops and negativity. He got his PhD last year?
Last year. Yes.
Last year from Caltech, working with David Simmons-Duffin. Please.
Okay, thank you. First of all, I want to thank you for the invitation. It's a great pleasure to be here. And today I want to talk about the work that I did with Julio Perro Martinez. And I should say, please, if you have any questions, feel free to interrupt me. So the motivation of this work is to understand this general question of what is the set of consistent theories of gravity, and perhaps a more concrete version of this question is what's the space of weakly coupled low energy theories of gravity that have a UV completion. So we know that at low energy, gravity is described by Einstein gravity, and we also know by EFT logic that you are allowed to have, or there should be higher derivative terms. That so this R, this Ricci scalar is giving the Einstein gravity, but we know that there should also be higher derivative terms that you can write down, and they will have some unknown Wilson constant that I wrote as alpha 2, alpha 4, etc. And so if you have a UV completion, the UV completion will give some predictions on these coefficients. But today I want to ask another question, which is there any constraints, any general constraint on these coefficients, just from the fact that the theory can be UV complete? So then we constrain the allowed size of these coefficients. And
Is there a particular reason you wrote C and not R?
Yeah, so because it's just some different contraction of like Ricci curvature, and also it's just they're basically R. And so it's known that there is indeed constraints, and then perhaps one famous example is this result by Kamenho-Eldestein on the Sena and Borodov. So the constraint basically comes from causality. So so in this work, the authors, they consider a scattering experiment where a graviton passes through a shockwave background, and when a graviton goes through this background, it's going to experience some time delay, which I rate right here as delta V. So because of causality, time delay had better be positive. You don't want things to come out before it comes in. So so this thing has to be positive. On the other hand, you can show that using this low energy action, you can show that the time delay schematically takes this form, where B is the impact parameter of the scattering. And so this plus and minus depends on the choice of polarization of your graviton. So if you stare at this, you'll see that if B is small enough, it seems like delta V can be negative, and which violates causality. And so that seems to be a problem. And the way this problem is resolved is that something has to break down when B is too small. And the authors argue that basically you will need some higher spin particle that shows up, and then basically the scale of B, the cutoff of B is set by the mass of this higher spin particle. And furthermore, these coefficients alpha 2, alpha 4, they have to also be suppressed by the scale of this higher spin particle. So you get some constraint like this, which says indeed the coefficient cannot be too big; they have to be suppressed by the scale of your higher spin mass. So, but there are several things about this argument that one might improve. So first of all, this is a parametric bound, which means you see these are tilde here. They are not sharp inequalities. So one might want to know, can you make this a sharp inequality with some computable numerical coefficients? And also, this argument only gives bound on 3-point couplings of gravitons. So this alpha 2 and alpha 4, they contribute to the 3-point graviton vertex, but you can also have like if you consider like a 4 graviton scattering, you can also have contact terms, and then yeah, then we don't know anything about them from this argument. And so there's another way. There is indeed another way of arguing constraints on this coefficient that would give you sharp bounds, and also it will give you bounds on also including these contact terms, and it's by using this dispersion relations. So I'll explain in detail the idea of this method, but basically this method gives you some sharp two-sided bounds on all the Wilson coefficients of your low energy EFT. So here I'm showing just one example from this paper where again they proved bound on this alpha 2 and alpha 4, same as what Kemp's did, and you see that you can just obtain a sharp prediction of the allowed region of the value of alpha 2 and alpha 4, and different colors means different space-time dimension, and so. And for those of you who live in 4 dimensions, you might notice there's no d equals 4 on this plot. And that's because in 4D, there are some higher divergence issue. So we'll discuss the case of d equals 4 separately. So here's the basic idea of dispersion equation. I'll give more details later, but let me just explain some basic here. So basically, using dispersion relation, you can write down some equation like this. And so where the left-hand side is some integral, this k is some kernel that you can choose. And this MEFT is just the amplitude of if your EFT, which you can just compute using your low energy calculations. So the left side is something you can compute in your EFT. The right-hand side is some UV physics, which we don't know. That depends on your UV completion. But what we do know is that you can always be written in a form like this, where it's a sum of some positive number times a known function fixed by symmetry. Okay. And the reason why these numbers are positive will follow from unitarity. And if you've heard about like conformal bootstrap or asymmetric bootstrap, you might recognize that this type of equation is perfectly suitable for using bootstrap methods. And basically you can from this equation, you can apply some bootstrap methods to extract some non-trivial bounds on this MEFT. Right? And this MEFT, since we are assuming a weakly coupled theory, usually people just insert some tree-level amplitude. Okay? But and that of course works, but one might wonder, can you add loops in this EFT amplitude? And a natural, yes.
So in this schematic presentation, it wouldn't matter for you that sum could be in principle infinite. So if you have, I can see the power of this method if you have a bunch of terms or you're going to truncate or something. But if formally that sum is like infinite sum, is it still going to be helpful, useful? Maybe you're going to tell us.
So yeah, so this sum is an infinite sum, but then formally, I guess it's hard to make statements about convergence of this sum because we don't know. That would require you knowing UV combustion. Yeah. And because yeah, so we don't know what this thing is. And so one thing you can try to do is that you can actually derive how this thing behaves at large energy using the fact that it has to reproduce this side, basically.
Okay, cool.
But yeah, maybe when I write down the precise form of the sum, it will be, So yeah, so one can ask, can you add loops in this amplitude? And of course the natural expectation is that of course you should be able to add them, and they should be computable, and they should probably be small. But it turns out that it's not. So that turns out to be true, but it's not as simple as one might have thought. And actually the original methods that were used to derive bounds at tree level would not work when you add loops, and you would need to use a different method. But eventually it will work, and that would be the topic of this talk. Yes.
I had a question for the previous slide.
Oh, yeah.
I noticed that the region that A to alpha to and alpha 4 can take is reducing with as you increase the dimension. Is that a general trend?
Yes, so that has to be true because of the way this is because we are obtaining constraints from this equation, and you can show that when this equation is true in higher dimension, it has to be true in lower dimension. So yeah. Any other questions? Okay. So yeah, so here's a brief outline of the talk. I will first review give some details of this method of dispersion relation, and also I'll show you how to derive bounds on at tree level, and then I'll add loop contributions. And as I said, you will need a different method, which is basically a new version of dispersion relation called crossing-symmetric dispersion relation. I'll also explain. And finally, I'll discuss the 4D case. But for the first two parts, let's assume D is greater than 4. So let's start with the first part. So let me start with my assumption. So I assume that I have a theory at low energy described by a weakly coupled EFT, and the cutoff that EFT I'll call lambda, and it's weakly coupled, so the G Newton times the cutoff raised to some appropriate power has to be much smaller than 1. Additionally, I'll also assume analyticity and crossing of the amplitude, which means that so the amplitude can have branch cuts on the real axis, but away from the real axis, it will be analytic. And also below the cutoff, when S, the Mendelssohn S is below the cutoff, you should be able the amplitude will just be given by whatever your EFT gives you. And finally, there is also Lorentz invariance and unitarity. So Lorentz invariance just means you can compose your amplitude into partial waves. So this PJ is what's called partial wave is some function fixed by Lorentz symmetry. It's some Geigenbauer polynomials, okay? And it has some unknown coefficients, which we don't know. So one thing we do know about this coefficient, this AJ, is that its imaginary part has to be positive, and that follows from unitarity. So
sorry, what's rho G?
It's the imaginary part of the
Physics of it.
physics of it. So
some sort of
yeah. So if you have like a state, just a particle at some high energy, and this will give you some Dirac function.
Is that sort of densive states?
Yeah.
Okay.
And finally, there's another assumption one has to make, which is the behavior of the amplitude at high energy, when energy is very large. And typically, what people usually assume is that when S goes to infinity, the amplitude has to grow, grow slower than S squared. So in a gap theory, you can prove this, but in a gravitational amplitudes, it's a little tricky. But in this talk, we're actually gonna just use a spin version of this condition. So this condition is for all values of t, Mendelssohn, which is like the transverse momentum. But you can consider integrating this amplitude against some wave packet, which is a function of p. And now you got a function that just depends on s, and then this wave packet. And you can choose this wave packet such that you have this property. And this basically follows from this assumptions on the previous slides, plus some physics about large impact parameter, which so for gravitational amplitudes at large impact parameter is described by some eikonal formula, which you can use to constrain the behavior at large S. So in this talk, I'll use this assumption. And the theory I'm going to consider today, so I'm not going to consider graviton scattering. I'm going to consider scattering of scalars, but the scalar is coupled to gravity. And so the scalar can have some action like this, where it have some higher derivative terms with coupling this G2, G3, and some higher coupling. Okay. And in the gravitational part, you can also have some non-minimal coupling between the scalars and graviton. And if you write down the amplitude of just the amplitude of 4 scalar scattering at tree level is just given by this, where the first term is comes from the graviton exchange, and then you have some contact term G2, G3 coming from these two terms in Lagrange.
In the plot with the colors, you have a mass of the higher spin field. Or not, that was
This one?
no, in the bound.
The bound.
Yeah,
this
you
one.
have M squared.
Yeah, so
I thought that was the higher spin field.
so yeah, so in the Kemp's argument, it is the higher spin field. If you use dispersion relation, it's kind of a scale you choose. Like like as long as below this scale, your EFT is valid, then you can then the method will work.
Put any higher spin field in there.
Right. So yeah, so this scale is like the scale where your EFT fits. Right. So yeah, so we have this tree level amplitudes, and later we'll also add one loops. But our goal will be to derive bounds on these coefficients G2 and G3. So let me explain. Let me explain the idea of dispersion relation. So basically, it's a relation that gives your amplitude in terms of the imaginary part of itself. And the way you can derive this equation is by looking at this contour integral. So you consider a contour integral that's along this blue contour. Yeah. And you can deform this contour and push it all the way to infinity, because away from the real axis is analytic, so you can just deform it. And I'm gonna choose the integrand such that at large S, it has some 1/s squared factor. And so if I choose that, then at infinity, the contribution just vanished because of this assumption I made about large S behavior. So this contour integral should give 0. On the other hand, you can separate this contour into 2 parts. One part, so you choose a scale M that has to be below your EFT cutoff, and then you separate one part. Right, so you separate it into this low energy part where the contour is below this scale M, and then some high energy part where it's just above the scale M. And the low energy part would just be something you can compute using your EFT. But the high energy part we don't know, but using Lorentz invariance, you can show that it can always be written in this form. So I'm introducing this bracket notation, which is just like integral against this rho of J. And again, from unitarity, this rho J has to be positive. And so one property of this bracket notation is that if the thing inside the bracket is positive, then the whole thing has to be positive. So this will be the only part, basically the only property that we will use for the high energy part.
So the bottom equation is a contribution of particular J to BST high.
Right. So this bracket you sum over J, and also you integrate over S prime. And so the whole thing will be a function of S and
bracket plus summation.
Yeah, sorry, yeah, so
Yeah,
the
yeah.
definitions. So yeah, so the equation will depend on S and T, because it comes from originally starting with your amplitude. So
Wait, that x prime to the power of 2 minus d over 2. Is there some way of understanding that? Is it some kinematic factor?
I think it's just a kinematic factor. It comes from let's see if I can see this.
Oh, I see. Okay.
Yeah, so
Yeah, there's a
there's a-
relation between the speckle density and the magnetic part. Okay. Yeah.
yeah, so this factor you would need it for the upper, but we'll just use that. It's because we'll just use positivity, so this factor actually wouldn't matter that much.
Mhm.
So yeah, so you get some equation like this, that depends on S and T. And you can further expand this equation, in essentially in S, but you want to extend in this because of crossing symmetry. But you can basically expand this to get a family of, I'll call sum rules that are labeled by some even integer. So here are the first two examples of these sum rules. So the sum rule always have this structure where on one side it only depends on your EFT couplings. So these G2, G3, etc. They're all couplings in your EFT and also the G Newton. And on the other side, it's some non-trivial sum of your high energy data. And the idea, so we have this relation, and what we now want to do is to extract some constraint on these coefficients using these equations, G2, G3. And the idea is to apply a functional. So these relations are a function of t, and the idea is to apply a functional that acts on this equation such that on the high energy side is positive. Okay, if you are able to find this functional, then that means the function acting on the low energy side also has to be positive. Well, you have to take care of some minus sign, but essentially you will get some inequality like this. And because the lower energy side is just you can write it down in terms of your EFT coupling, this becomes some constraint on your EFT coupling. And one typical example of such functional is by expanding it around t equals 0, which people call the forward limit. So let's just consider one simple example. So let's first assume we don't have gravity. So G Newton is 0. And if you go back to this coupling, we go back to these sum rules and we forget about this G Newton. And if you just take t equals 0, if you take t equals 0, on the left-hand side, you just get G2 here. And for this sum rule, you just get G4. And on the other hand, on the other side, if you take t equals 0, the thing inside the bracket would just be positive. So it would just be m squared to some power, which is a positive number. And the bracket, if the thing inside the bracket is positive, the whole thing is positive. So you would just get G2 is equal to something positive. And similarly, from this sum rule, if you take t equals 0, you'll get G4 is equal to something positive. So that gives some relation like this, basically, which means all these couplings, G2, G4, G6, with even integer, they all have to be positive. And this is a very well-known result. I think for maybe well, one which is written in this Adams et al. Paper. So, but this result just comes from taking the t equals 0 limit. You can do more sophisticated things like combining derivatives around t equals 0. And if you make some clever choice of these functional, in general, you can prove some these two-sided bounds, this one. So all the GK couplings has to satisfy some two-sided bound, whereas and you will have some scaling with m, the scale you choose for your dispersion relation, and just follow some dimensional analysis, and then you'll have some computable numerical factor in this inequality. Yes.
This is also true for G is equal to 0, the last equation.
Is it also true for?
Like, is that for assuming G is equal to 0, or is that?
Oh yeah, this is sorry. Yeah, this is assuming G Newton is 0. Yes.
Hey, can you just a little bit, if we zoom out a little bit, what is the origin of this positivity? So the positivity comes from is some statement about the amplitude.
Yeah.
Can I understand that in terms of correlation functions?
Correlation functions.
I mean, correlation functions, if they have some sort of like, sometimes you could say 4-point function has this, for example, positivity if you put this delta half or J operation. Like, are these related at all?
Let me think. So
I understand that this is a very high level and big question, but
But I think in a general sense, it's always related to positivity of the scalar product in quantum mechanics.
yeah, but I'm trying to say if
Yeah.
at this level, there's one step we could make.
You were saying unitarity and.
Right, but like that positivity of inner product, for example, in one particular example, can we relate this to like 4-point function? You could cook up setups where it's just a norm,
yeah.
and then that has to be positive. So it's positivity of that. But in between that and this, there are many steps. And
Yes. So I'm not sure if this will answer. I think in ADS CFT, you can relate these positivity bound in the bulk to some positivity bound on the 4-point function of their CFT.
Okay.
So I think that's possible.
So the scattering in the bulk corresponds to correlator and the bound.
Yeah.
Okay, good. Thank you.
So right. So now let's add back G Newton, and so the only place where G Newton show up is in this sum rule. It's B2 sum rule, and you see that after you add back this term, you cannot take t equals 0 anymore because of this 1 over t term, and so the solution of this problem is that you just don't set t equals 0. Instead, you look at the sum rule at the fixed impact parameter. So this might remind you of this Kemp's argument that I showed earlier, where they consider scattering a fixed impact parameter. Here you are doing a similar thing, and basically what you will do is that you integrate this function against. So you integrate the equation against the function f of p, and it's a function of the transfer momentum. T is minus p squared. And you choose this function such that its Fourier transform is localized at some fixed impact parameter. And if you do that, you can show like the contribution of this term would just be, well, it just be suppressed by this scale. And if so, the idea is to just get something, you just want to suppress this term such that it won't give you divergences. But if you do this, you encounter another problem. So, which is after you do this integral, you get the non-zero contribution for each term. So previously, if you set t equals 0, all these terms just disappear, and you just get one term, and also the system. But if you do this integral, all these terms will contribute. So you just get and you just get an infinite sum. So you just get an inequality with some infinite sum, and it's not clear what that means. So, but again, fortunately, there's again another solution. The idea is that you can come up with a sum rule that only has finitely many terms, that just doesn't have infinite sum. And the way you can write down these sum rules is by using crossing symmetry again. So let's look at these two summaries again. So this is the summary that we were studying. And then remember, we also have this summary. And you will notice that this G4 coupling shows up twice. It shows up here and it shows up here. And this is because, so basically this summary, you can think of it as probing the coefficient of s squared in your amplitude. And this summary is like probing the coefficient of s to the fourth in your amplitude. And so the reason why G4 shows up here is because in your amplitude, you have a term which is like G4 times s squared times t squared. And the reason why G4 shows up here is because in amplitude, you have G4 times h to the fourth. And the fact that it shows up in these two combinations follows from crossing symmetry, because it has to appear in this form. Yeah. And so that means you can basically take this B2 summary and then just subtract the t equals 0 limit of this summary, and then that will just remove this term. So basically, so if we look at the first two terms, B2 minus this term would basically remove this G4 somewhere. And you can keep doing this, and it will just remove all of them. And this gives you on the low energy side, well, it would just give you a finite sum. And on the high energy side, so on this side, this improved sum will also give you something in closed form. Well, the thing in the bracket would be in closed form. So so now you use this improved.
So the thing in the bracket would itself be an infinite sum, right?
It will be an infinite sum, yeah, but it will be an infinite sum with will be an infinite sum of some known expression times some positive number. Times
So
some
you're gonna have
positive
a
factor.
doubling sum. That's
Oh no, so sorry. So this infinite sum you can do in closed form. Like it will be an infinite sum of things like this. And you can just
No, I understand, but
evaluate
like I'm
that.
saying, on the right hand side, you have a double infinite sum because your bracket notation is hiding one sum over J.
That's true, yeah. Yeah, that's true. Yeah, but the idea is that it will be an infinite sum of,
Yeah,
we want to use it such as an infinite sum of positive number.
yeah, still positive holds.
Yeah. So yeah, so if you do that using this improved summary, you can now obtain bounds on these G2 and G3 couplings, and they'll be in terms of this in terms of G Newton. So here on this plot, again, different colors means different dimension. You can kind of just look at d equals 5, and so the horizontal axis is G2 divided by G Newton, where the vertical axis is G3 divided by G Newton. And one thing you will notice is that now G2 is allowed to be negative, whereas previously without gravity, G2 has to be positive. And one intuition is that the reason why without gravity you cannot have negative G2 is because it leads to time advance, but gravity itself has time delay. So with gravity, you're allowed to have a little bit of negativity, but it has to be suppressed by G Newton. And on the other hand, if you look at these higher couplings, this G4, G6, etc., they will still satisfy positivity bound.
So can you say a few words about how these plots are obtained a little more detail? So you have the expression above is equal to this awfully infinite sum.
Yeah.
But functions, some positive coefficients that you do not know a priori, but some known functions as in the sum.
Yes.
And somehow you massage that into this.
Yes. I wish I can write things down.
Sorry about that.
Let's see. Yeah.
So for example, can you highlight the dimensional dependence on D? How does that come about?
So yeah, so the dependence on D is hidden here in this function. So this function is fixed by Lorentz symmetry, and so it depends on D. So that's where the D dependence comes in.
All right, so this one we can talk offline.
Yeah, and right, okay. And right, so that's the tree level bound. And now let me discuss how to obtain bounds after you add one loop corrections. So the idea is basically you have your EFT amplitudes. Originally you use the tree level amplitude. Now the first step it would just be add the one loop contribution in the amplitude. So the first step is to just compute the one loop amplitude. And so the method is pretty standard. Maybe I'll just use this one slide to explain. Basically you compute it using the method of unitary cut. So that you can obtain one amplitude by gluing together different tree level amplitudes. So you can glue so the solid lines are scalars. So you can have like 4 scalars, but you can have like 2 scalar, 2 graviton scattering. And you also need to like glue them together. And in this case, it will be graviton that's in the loop. But eventually you'll get some expression. This I are some standard integrals of your loop integral, and then you have some functions of Mandelstam. So the exact form is not important, but I would one thing I would like to emphasize is that you will always get this type of box integral, and this box integral gives a problem. Basically, it comes from a diagram like this, where in the four scalar amplitude, you can have some graviton extremes like this. And for this box integral, if you look at the t goes to 0 limit, it would have some logarithmic divergence near t equals 0. And this means that for all the sum rules, you will find that you cannot take t equals 0 limit because of this log. And this is problematic because if you remember previously for the tree level argument, we have to define this improved sum rule such that we only get finitely many terms. The definition of that improved sum rule requires evaluating these higher sum rules at t equals 0. And at one loop amplitude, they all become ill defined. But if you also you can also recall that the reason why we are able to do this improved sum rule is because of crossing symmetry. So the reason why we can have this cancellation is because our lower energy amplitude has some crossing symmetry, so that we can take a certain linear combination to cancel the same component. And so essentially what we will need to do to solve the problem is that we want a way to impose crossing symmetry, but we don't want to impose it by taking t equals 0. And fortunately, there is a way to do it, and it's by using what's called the crossing-symmetric dispersion relation. And the idea of crossing-symmetric dispersion relation is that your amplitude, your amplitude has to be crossing-symmetric. And so instead of writing your amplitude in terms of the usual Mandelstam, you can just write it in terms of some manifestly crossing-symmetric variable. And so the variables are defined as, so I'm calling them x and a. They are, as you can see, manifestly crossing symmetric. And one thing I would like to point out is that near the forward limit, a is basically t. So when t is very small, a are basically t. So you can think of a as some crossing symmetric version of t. And it'll play a similar role as at t later. And if you take a tree level amplitude, you can indeed write it in terms of this variable x and a. And there is an important constraint that I'll call locality constraint. So if you consider a term like this, x to some power times a to some power, and you write it back in terms of Mandelstam, you get something like this. But if this term is from a contact term, you wouldn't have anything in its denominator. That means m has to be less than or equal to 8. So the power of a cannot be greater than the power of x for any contact terms. And that is indeed true in this equation. You can just check that in all the terms the power of a is not greater than power of x.
I'm missing the intuition. Why is that m has to be less than n? Because in contact term that cannot be heard for the
it's I mean the contact term is it would just be some derivatives acting on So it's not from some
Yeah,
exchange
yeah,
of
yeah.
particles. So
Sorry,
yeah.
of course. The convection always has that.
And so this is what the amplitude looks like, and then you can also derive a dispersion relation in terms of this this variable x and a. It takes a similar form. So maybe yeah, it's a bit technical, so maybe I wouldn't, yeah, maybe let me not spend too much time on this. So one comment is that it follows from almost the same assumption, but it requires a slightly stronger analyticity condition. So you would also want some analyticity even for a complex T. But but if you assume that, you can indeed derive this kind of relation. And again, the idea is similar. You separate the contour integral into a low energy part, which you can compute within your EFT, and then some high energy part, which is a sum of a positive sum of known functions. And
So sir, what's the meaning of twice subtracted?
yeah, so twice subtracted. So I have to go back here. So twice subtracted follows from this this condition, because so the idea of dispersion relation, you want to push the contour to infinity, and then you want that contribution of infinity to vanish. So in the integrand, you will want some factor like this. You wouldn't, you cannot have just the amplitude itself. So sorry. Yeah. So that's why in this relation, in the integrand, you have m over this. So this factor is what we call subtraction. Like,
Yes.
you write, you cannot write m as the integral of the imaginary part of the cell. You can only write m over s squared as the imaginary part of the cell. And
That was the twice subtracted?
twice, because you have 2 powers of s in the denominator. Yeah. So like if you only have like m over s, it's like once subtracted.
Do you ever use that?
So in some like large n theories, sometimes people can argue it. You can use it. And okay, here. So yeah, so this is the relation, and you can expand it to get a family of sum rules. And the low energy contribution just look like this. Okay. And one thing you'll notice, so first comment is that this is like measuring the scattering at fixed A instead of at fixed T. And one thing you'll notice is that automatically it would just give you a finite sum. It doesn't have an infinite sum. And this is because of this locality constraints that we discussed earlier. So this sum is like looking at the coefficient of x in your amplitude. And because you cannot have x times a squared, that will violate causality constraints. In this sum rule at tree level, you would just get this, and similarly for the others. So there's no need to improve the sum rule. The sum rule itself is just automatically improved. It would just have finally imaginary, because it has crossing symmetry built in. But then you can do the same thing. You apply a functional, which is like an integral over a against some function f of p, which you can choose. And another comment is that the range of a is a bit tricky. So if you remember, a is defined in terms of these Mendelssohn STU, and if you demand that this STU all are within the EFT region, so they're below the cutoff, it turns out that the value of a has to be minus m squared over 3. So there's some funny factor of 3 in the value of a. Yeah. And so yeah, so maybe let me go back. So we have this sum rule, which just says that the low energy part, this whole thing has to equal to the high energy part, which is some, this bracket notation. And we know what the low energy part looks like. And what you want to do is that you want to apply this functional such that in the high energy part, so this high energy part, it would be an infinite sum of this thing, is this C2. And you want to choose the function, choose this function f of p such that it's positive for all values of m above the cutoff and for all values of j. So this bracket notation would be an integral of m and an infinite sum of j, and you just want the external function on it to be positive for it in the entire region of this intervals. And if you are able to find such a functional, then you can show that then you would just get the low energy part has to satisfy an inequality, and that gives you constraints on G2 and G3. And there's another thing that you can add, which is called the null constraints that that again follows from crossing symmetry. So remember that if you look at this, so here we're using this C2 sum rule, just like this leading sum rule, but you can also add in these two sum rule or even the higher ones. But you on the other hand, but you don't want to put in more couplings because let's say you're only interested in G2 and G3. So the idea is that you can put this in, but then you choose a functional such that it just kills any expression of this term. But on the other hand, on the high energy side, it will still be a non-trivial constraint. So the fact that the high energy sum has to reproduce exactly an expression of this term is again some non-trivial constraint, and you can put that in. That's called the null constraints. So if you do all these things, so the non-trivial thing is to find this f of p, such that this condition is satisfied. But this is something you can solve numerically, and so if after you do that, you'll again get some bound like this. And I should mention, so originally this fixed t bound, which the previous one I showed, is also derived in a similar way. And so eventually you'll get some plot like this, and the fixed A plot is the one using crossing symmetric sum rules, and the fixed T plot is just the same plot that I showed before. And you'll notice that the fixed A plot, the fixed A bound is weaker, and this is so this is we don't fully understand why it's weaker. One way you can think about it is that you're kind of using a smaller space of function, because here the allowed range of A is there's some funny factor of 3, whereas if you do in the fixed T case, you can just integrate up to m squared. So numerically, it's kind of clear that why it's weaker, and but physically, it's not so clear. But recently there's some work that shows if you just force your value of A to go all the way up to m squared, so you force your value of A to go all the way to EFT cutoff, you indeed get the same bounds. But in order to do that, you need to allow for some you need to allow your scattering angle to be imaginary. So yeah. But the point is, the reason why we want to do it in the fixed A, because so this is 3-level bound, and if you add one loop corrections, the fixed T bound will just get divergence. But for fixed A bound, you'll have some finite one loop corrections. That's why we want to go to the fixed A. And so before I show you what the one loop corrections look like, let me just, I guess I have like 10 minutes left. Okay. Let me quickly mention some comments on the one loop part. So remember that we have this issue that after applying the sum rules, we will get an infinite sum of EFT series, and this also happens at one loop. And at 3-level, you can make this sum finite by either use the improved sum rules at fixed T or using the crossing symmetric sum rules, which is automatically gives you finite sum at 3-level. But at one loop, it seems like it always gives you an infinite sum. At least to my knowledge, I don't know if there's a way to give finite sum at one loop. And so the best you can hope to do is that you would just truncate this sum, and then you have to make some estimate for the thing you store away. that makes an estimate of the error, and that requires knowing the size of these GKs at large K, which is an interesting problem on its own. And there have been some bounds that obtain up to K equals to 10, and presumably even at parametrically large K, you can obtain some analytic bounds. But we're not gonna do that here. Here we're just gonna assume that they are separated by some order 1 coefficients, and then so we'll have some estimate for the error, but the error will have some unknown order 1 coefficients. And so if you do that, you can indeed compute one loop corrections and to your bound. And so this is the plot for this G2, G3 plot. And so depending on the value of G Newton, you would just get different corrections. And one comment is that because we're at one loop, coupling can run, so we're just choosing the normalization scale to be the same as this cutoff scale. And the title of the talk, negativity, comes from this observation, which is the fact that even with gravity, we find that this G2 and some roots, these G4, G6 couplings, they are also positive. But at one loops, all of them are allowed to be a little bit negative. But the negativity would be suppressed by G Newton squared. So you can have the same intuition, which is that negative G4 and G6 lead to time advance, but gravity still gives you time delay. But for these higher couplings, the effect will start at one loop. You wouldn't see it at true level. Okay. So finally, I want to discuss what happens at 4D. Let me maybe try to be quick. So again, let's look at this somewhere again. So the idea, recall that the idea is that you want to apply this functional such that at high energy side is positive. On the other end, if you can find it, you will get some inequalities on the lower energy side. But it turns out that in 4D, it's impossible to find such function such that the high energy side is positive and the lower energy side is finite. So so it seems like such FMP cannot exist. And one resolution is so one way you can solve it is just by introduce some IR regulator, and you can use just some IR cutoff. But here I'm using dim reg. So if you insert some p to the d-4 here, you can still get a bound, but you'll be proportional to 1 over d-4. And so you get some IR divergent bound. But so this is what you get at tree level. You can imagine doing it at one loop. And at one loop, there are two sources of IR divergences. So there are IR divergences in the amplitude itself. At one loop amplitude in 4D has IR divergence. And also the action of this functional, when you act it on one loop amplitude, it also has IR divergences near the p equals 0 limit. And it turns out that the correct limit to reproduce these two divergence would be you take a goes to 0 and d goes to 4 simultaneously, but you'll want to fix this a to the d-4. And if you do that, you'll indeed get some one loop correction, which is proportional to G Newton squared, and now it's a double pole. You'll get 1 over d-4 squared. And you can even do this higher loop. And so the observation is that these IR divergences come from this limit, and the behavior of gravitational amplitude in this limit, in particular, the limit where a goes to 0, which is like the forward limit, the behavior of gravitational and forward limit is known. It's described by the eikonal amplitude, and you can use this amplitude eikonal formula to describe the behavior in this limit actually at all orders in G. The leading IR divergences. So you can try to use this formula to resum all these IR divergences. And what you'll find is that so it is this plot. So this plot I'm plotting basically the bound in terms of versus this d-4 over G Newton, and it says so it's a function of G Newton and D, and D minus 4 you should think of it as your IR cutoff. And if you expand this at small G Newton, which is like in this region, then the two results agree. The fixed order result and the result using eikonal formula agree. But if you expand it at D equals 4 first, so you take the IR cutoff to 0 first, then the fixed order result is diverge. But it turns out that for the eikonal formula, you'll get something finite. So you seem to get a finite bound even at D equals 4. So G2 has to be greater than some negative number. But there's another problem of this bound, though this bound is not suppressed by G Newton. So you can ask, we have two versions of bounds on G2, and you can ask which one is better. You have a bound like this, and you have a bound like this. So here I'm switching to IR cutoff in the integral. So 1 over D minus 4 basically becomes this log of MIR. So you can ask which one is better, and it turns out that the suppression from G Newton is a much bigger effect. So for example, if you take M, this M is like a cut of your EFT. If you take it to be like even at some like glider scale, like 100 TeV or even higher, and you can take this MIR to be the Hubble scale, and you'll find that this log is like a factor of 100 or 200. But the suppression from G Newton is a much smaller number. So if you just plug in some number here, you'll find that this number is much smaller than this number. Well, sorry, the absolute value of this number is much smaller than the absolute value. So in practice, this is still kind of a better bound if you have some physical input for the IR cutoff. And another place you can think about this bound is in ADS CFT, where you have a natural IR cutoff, which is the ADS radius. And so in that case, you'll basically get some bound like this, where this log just becomes a log like this. And the analysis calculation for this bound is not done, but the expectation to that is that if you go to higher orders in G Newton, you'll get some higher logs like this, and if you resum all the logs, you should get something finite like this. So so it'll be a competition between your values of RADS and your values of G Newton. And ideally, what you will want to do is, of course, replace this IR cutoff with some physical scale. And a natural expectation is to replace this cutoff with the scale where the eikonal approximation breaks down. So I think the most ideal case would be of some bound like this, where this MIR would just be replaced by the scale where the eikonal breaks down. And if you have some stringy models, in this work, the authors they predict that this scale will be given by something like this. So if you plug this in, you'll find that you can almost get a bound as good as once you get in higher dimensions. It'll be G2 is greater than or equal to minus G Newton over M squared, but then you have some logarithmic answer.
The square root of log.
I think that's square root of log if I copy it correctly.
Square root of log.
Yeah. So I guess I'm out of time, which is a good place to wrap up. And so let me just summarize. So hopefully I've shown you that how to incorporate loops in EFT into this methods of using dispersion relation to bound gravitational EFTs. And I showed that you have to introduce another dispersion relation called crossing-symmetric dispersion relation to compute the one loop corrections. And finally, we observed that if you use the eikonal amplitude, simply you can describe the leading IR divergences of the bounds in 4D, and that allows you to resum this divergence. And some future direction will be to generalize this for graviton scattering, because so far we've discussed for scalar scattering, and it would be nice to do actual graviton scattering. And also, as I mentioned, you can study similar problem in ADS CFT. And in this case, the dispersion relation will be some CFT dispersion relation, which is more rigorously derived. And there's an analogous story in the Pion bootstrap where you assume some you have some larger in QCD, and then you can basically do the same thing to constrain the pion scattering at low energy. And in that case, there's you can ask the similar question: can you include 1/n corrections? That would be the analogous one loop effect, and yeah. And finally, it would be nice to improve this Fourier argument with more physical input, and hopefully replace the IR cutoff with a physical scale. I'll stop here. Thank you.
More questions?
How to determine the EFT cutoff from lower to higher?
Right. So it's like an input, right? So you said if my EFT had this cutoff, then the coupling in an EFT has to be suppressed by a computational number divided by the cutoff raised to the appropriate power.
And does it
I just have a naive question. So the key idea was this expression that, at least on the right-hand side, the UV part involved an infinite sum.
Yeah.
You sort of pushed under the rug that this sum is well defined, is convergent, everything's fine. Should I be worried about that, or?
Yeah, well, you're worried that an infinite sum of positive number, if it doesn't converge, it could
I mean, if I had some sort of I was working with CFT or something, I said that there is some sort of control. But these are EFTs.
These are EFTs, yeah.
So a priori, well, unless there's some sort of physics argument, I don't know that these sums will be well defined and convergent and nice. They could be asymptotic, they could be whatever. I actually don't know. I have no idea what they would behave like.
So there's a sum over J, and then there's a sum or integral over the mass or the S. I think the sum over J is more or less controlled because that's just that's partial wave decomposition. This integral over mass, I agree, it's not clear if it's gonna converge or not. So yeah.
Okay, thank you so much. Any last questions? Not, let's thank again.